Article 250.136b of the National Electrical Code states that exposed non-current carrying metal parts of motor frames shall be grounded. This means motor frames should be bonded to the grounding system of the facility. Ground loops can occur when there is more than one path for ground current to flow. However, bonding motor frames to the building steel does not create ground loops. The grounding conductor provided for the motor ensures that fault current will take the intended path back to the source, preventing the creation of ground loops. Bonding motor frames to the building steel provides several benefits. Firstly, reduced voltage gradients are realized. Bonding the motor frames to the steel structure helps distribute fault current over a larger area, reducing voltage gradients and the risk of shock hazards. Secondly, improved grounding performance occurs. A well-bonded steel structure acts as a low-impedance grounding path, ensuring a reliable ground return for fault currents. Thirdly, compliance with codes is achieved. Bonding motor frames to the building steel is required by the NEC and other electrical codes to ensure the safety of personnel and equipment. Instructions not to bond the motor frames to the building steel are not in compliance with the NEC. Article 250.136b clearly states that motor frames must be grounded, and bonding them to the building steel is an effective and common method of grounding. It is correct to bond motor frames to the building steel if the facility has a well-bonded steel structure. This practice improves grounding performance, reduces voltage gradients, and complies with electrical codes. The instructions to avoid bonding the motor frames are incorrect and violate the NEC requirements. Bonding motor frames to building steel is a critical aspect of electrical safety and code compliance. This practice ensures that motor frames are properly grounded, minimizing the risk of electrical hazards and ensuring the reliable operation of equipment. The National Electrical Code, or NEC, specifically addresses the requirements for grounding motor frames in Article 250.136b. This article mandates that exposed non-current carrying metal parts of motor frames must be grounded. This requirement is not merely a suggestion, it's a fundamental safety measure designed to protect personnel and equipment from electrical faults. The purpose of grounding motor frames is to provide a low-impedance path for fault current to flow back to the source in the event of an electrical fault within the motor. This low-impedance path ensures that the fault current is quickly cleared, preventing the build-up of dangerous voltage levels on the motor frame. When a fault occurs, the current flows through the grounding conductor back to the source, tripping a circuit breaker or blowing a fuse, thereby isolating the faulty circuit and preventing further damage or injury. The concept of ground loops often arises in discussions about grounding and bonding. Ground loops occur when there is more than one path for ground current to flow, creating a circulating current that can cause interference and other electrical issues. However, bonding motor frames to the building steel does not create ground loops. The grounding conductor provided for the motor serves as the primary path for fault current to return to the source. This conductor is specifically designed to handle fault currents and is sized according to the requirements of the NEC. When the motor frame is bonded to the building steel, it simply provides an additional path for fault current to flow, enhancing the overall grounding system. The presence of multiple grounding paths does not create a ground loop because the fault current will always take the path of least impedance back to the source. The benefits of bonding motor frames to building steel are numerous and significant. Firstly, it reduces voltage gradients. Voltage gradients occur when fault current flows through the earth or the building structure, creating a difference in potential between different points. This difference in potential can pose a shock hazard to personnel who may come into contact with the affected areas. By bonding motor frames to the building steel, fault current is distributed over a larger area, reducing the voltage gradients and minimizing the risk of electric shock. Secondly, it improves grounding performance. A well-bonded steel structure acts as a low-impedance grounding path, ensuring a reliable ground return for fault currents. This low-impedance path allows fault current to flow quickly and efficiently back to the source, minimizing the duration of the fault and preventing the build-up of dangerous voltage levels. A robust grounding system is essential for protecting equipment from damage and ensuring the safety of personnel. Thirdly, it ensures compliance with codes. Bonding motor frames to the building steel is required by the NEC and other electrical codes to ensure the safety of personnel and equipment. These codes are developed and maintained by experts in the field of electrical safety and are based on years of experience and research. Compliance with these codes is not optional. It's a legal requirement that must be followed to protect the safety of workers and the public. It is important to note that instructions not to bond motor frames to the building steel are not in compliance with the NEC. Any advice or instructions that contradict the requirements of the NEC should be carefully scrutinized and verified with a qualified electrical professional. Article 250.136b clearly states that motor frames must be grounded, and bonding them to the building steel is an effective and common method of grounding. Ignoring this requirement can have serious consequences, including increased risk of electrical shock, equipment damage, and code violations. In conclusion, it is correct to bond motor frames to the building steel if the facility has a well-bonded steel structure. This practice improves grounding performance, reduces voltage gradients, and complies with electrical codes. The belief that bonding motor frames to building steel creates ground loops is a misconception that should be dispelled. A properly designed and installed grounding system, including the bonding of motor frames to building steel, is essential for ensuring the safety and reliability of electrical systems. Let's delve deeper into the technical aspects of grounding and bonding motor frames to building steel, examining the specific requirements and best practices that ensure electrical safety and code compliance. First, let's discuss the NEC requirements in detail. Article 250.136b of the NEC, as previously mentioned, mandates the grounding of exposed non-current carrying metal parts of motor frames. This requirement is further elaborated in other sections of Article 250, which provides specific guidance on how to achieve proper grounding. The NEC defines grounding as the connection to earth of a circuit conductor or equipment enclosure. The purpose of grounding is to provide a low impedance path for fault current to flow back to the source, thereby tripping a circuit breaker or blowing a fuse and isolating the faulty circuit. Grounding also helps to stabilize voltage to earth during normal operation and limit the voltage rise due to lightning or other transient events. Bonding, on the other hand, is the permanent joining of metallic parts to form an electrically conductive path that ensures electrical continuity and the capacity to conduct safely any fault current likely to be imposed. Bonding is essential for creating a lower impedance path for fault current and minimizing the risk of voltage gradients. When it comes to motor frames, the NEC requires that they be bonded to the grounding system of the facility. This can be achieved in several ways, including using a grounding conductor run with the circuit conductors, bonding to the building steel, or using a combination of both methods. The size of the grounding conductor must be determined in accordance with Table 250.122 of the NEC, which specifies the minimum size of the grounding conductor based on the size of the overcurrent protection device protecting the circuit. It's important to note that the grounding conductor must be installed in a manner that provides a continuous and uninterrupted path back to the source. This means that the grounding conductor must be properly connected to the motor frame, the building steel, and the grounding electrode system. The grounding electrode system is the means by which the electrical system is connected to the earth. The NEC requires that all electrical systems have a grounding electrode system that consists of one or more grounding electrodes. Common types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. The grounding electrode system must be installed in accordance with the requirements of Article 250 of the NEC. In addition to the NEC requirements, there are also industry best practices that should be followed when grounding and bonding motor frames to building steel. These best practices are based on years of experience and research and are designed to enhance electrical safety and reliability. One important best practice is to use exothermic welding, also known as CAD welding, to connect grounding conductors to building steel. Exothermic welding creates a permanent, low-resistance connection that is resistant to corrosion and vibration. This type of connection is far superior to mechanical connections, such as bolted connections, which can loosen over time and increase resistance. Another best practice is to use a dedicated grounding conductor for each motor. This ensures that each motor has its own low impedance path back to the source, minimizing the risk of voltage gradients and improving grounding performance. When multiple motors are located in close proximity, it's often more practical to use a common grounding conductor that is sized to handle the combined fault current of all the motors. However, it's important to ensure that the common grounding conductor is adequately sized and properly installed. In addition to grounding and bonding, it's also important to perform regular inspections and testing of the grounding system. This includes visual inspections to check for loose connections, corrosion, and damage to grounding conductors. It also includes testing the resistance of the grounding system to ensure that it meets the requirements of the NEC. A ground resistance tester can be used to measure the resistance of the grounding system. The NEC does not specify a maximum ground resistance value, but it's generally accepted that a ground resistance of 25 ohms or less is considered acceptable. However, in some cases, a lower ground resistance may be required depending on the specific application and the requirements of the local authority having jurisdiction. It's also important to consider the impact of harmonics in the grounding system. Harmonics are non-sinusoidal waveforms that can be generated by electronic devices, such as variable frequency drives, or VFDs, and other nonlinear loads. Harmonics can cause increased current flow in the grounding system, which can lead to overheating and equipment damage. To mitigate the effects of harmonics, it's important to use appropriate filtering and grounding techniques. This may include using harmonic filters, oversizing grounding conductors, and using isolated ground systems. In conclusion, grounding and bonding motor frames to building steel is a critical aspect of electrical safety and code compliance. By following the requirements of the NEC and implementing industry best practices, it's possible to create a safe and reliable electrical system that protects personnel and equipment from electrical hazards. Regular inspections and testing of the grounding system are essential for ensuring that it continues to function properly over time. Remember, electrical safety is not just a matter of compliance, it's a matter of protecting lives and property. The importance of proper grounding and bonding cannot be overstated, and it's essential that all electrical professionals have a thorough understanding of the principles and practices involved. Let's now delve deeper into the specific scenarios where bonding motor frames to building steel is particularly crucial and address some common misconceptions that may arise. Firstly, in industrial facilities with extensive steel structures, bonding motor frames to the building steel is often the most practical and effective method of grounding. The steel structure itself acts as a vast grounding grid, providing a low impedance path for fault current to flow back to the source. This is especially important in large facilities where long runs of grounding conductors may introduce significant impedance. By bonding motor frames to the building steel at multiple points, the overall impedance of the grounding system can be significantly reduced, improving its effectiveness. Secondly, in hazardous locations, such as those where flammable gases or vapors are present, proper grounding and bonding are even more critical. In these environments, even a small spark can ignite a fire or explosion. The NEC has specific requirements for grounding and bonding in hazardous locations, which are outlined in Article 500 through 516. These requirements include the use of intrinsically safe equipment, explosion-proof enclosures, and specific grounding and bonding techniques. Bonding motor frames to building steel in hazardous locations helps to minimize the risk of static electricity buildup and provides a low impedance path for fault current to flow, reducing the likelihood of a spark occurring. Thirdly, in facilities with sensitive electronic equipment, such as data centers and hospitals, proper grounding and bonding are essential for preventing electrical noise and interference. Electrical noise can disrupt the operation of sensitive electronic equipment, leading to data loss, equipment malfunction, and even system downtime. Bonding motor frames to building steel helps to create a clean and stable ground reference, minimizing the effects of electrical noise and interference. In these types of facilities, it's often necessary to use isolated ground systems, which are specifically designed to minimize electrical noise. An isolated ground system is a grounding system in which the grounding conductor is isolated from the building steel and other grounded metal parts. This helps to prevent electrical noise from propagating through the grounding system. Now, let's address some common misconceptions about bonding motor frames to building steel. One common misconception is that bonding motor frames to building steel will create ground loops. As previously explained, ground loops occur when there is more than one path for ground current to flow, creating a circulating current that can cause interference and other electrical issues. However, bonding motor frames to the building steel does not create ground loops. The grounding conductor provided for the motor serves as the primary path for fault current to return to the source. This conductor is specifically designed to handle fault currents and is sized according to the requirements of the NEC. When the motor frame is bonded to the building steel, it simply provides an additional path for fault current to flow, enhancing the overall grounding system. The presence of multiple grounding paths does not create a ground loop because the fault current will always take the path of least impedance back to the source. Another common misconception is that bonding motor frames to building steel is not necessary if the motor is already grounded through the equipment grounding conductor. While it is true that the equipment grounding conductor provides a path for fault current to flow back to the source, bonding the motor frame to the building steel provides an additional layer of protection and enhances the overall grounding system. Bonding to the building steel helps to reduce voltage gradients, improve grounding performance, and ensure compliance with codes. It's also important to remember that the equipment grounding conductor may not always be the most effective path for fault current to flow, especially in large facilities with long runs of conductors. In these cases, bonding to the building steel can provide a more direct and low impedance path for fault current. Another misconception is that bonding motor frames to building steel is only necessary for large motors. While it is true that larger motors may generate more fault current, it's important to bond all motor frames to the building steel, regardless of their size. Even small motors can generate enough fault current to pose a shock hazard, and bonding to the building steel provides an additional layer of protection. It's also important to remember that the NEC requires that all exposed non-current carrying metal parts of motor frames be grounded, regardless of their size. In conclusion, bonding motor frames to building steel is a critical aspect of electrical safety and code compliance. This practice enhances the overall grounding system, reduces voltage gradients, improves grounding performance, and ensures compliance with codes. Common misconceptions about bonding motor frames to building steel should be dispelled, and all electrical professionals should have a thorough understanding of the principles and practices involved. By following the requirements of the NEC and implementing industry best practices, it's possible to create a safe and reliable electrical system that protects personnel and equipment from electrical hazards. Remember, electrical safety is not just a matter of compliance, it's a matter of protecting lives and property.